All right, so we'll begin by looking at part one, which is unit three. So we need to understand that everything is made up of matter and energy. So in this video, I will talk about how we measure both, how we measure matter and energy. So when we talk about measure, so how do we quantify things? I give examples here. We can use a scale, we can use a ruler, we can use a thermometer, we can use some measuring cups or something to measure volume. We can count, right? So there's several ways where we can measure things. It really depends on two things. It depends on if we're talking about whether it's matter or energy, obviously, but then also quantity. You wouldn't measure pounds and pounds of I don't know flour in a tiny little scale, right? So the amount does matter in terms of how you're going to quantify it. And then physical state, it depends if it is a solid, a liquid, or a gas. We would measure them differently. So solids we usually measure using measuring their mass or their weight. Weight takes under consideration gravity, so a lot of times we just use the word mass. We measure in grams, and this is the abbreviation for grams, and we usually use a scale. Volume, if we're talking about pure liquids, meaning that liquids that are mixed with anything else, we usually measure in liters. In other words, we measure in volume, right? So the amount of space that something occupies. Um, and the unit that we use is liters and is abbreviated as this capital L. Now, if the liquid, or actually the fluid, it's better said because it could be gases as well. If the fluid is a mixture of different substances, then we need to take into consideration concentration, which is the ratio of the amount of the smaller particle in there. We call them the solute per solution, per volume of solution. So it is a ratio if we're talking about mixtures. Okay, so the other way that we can measure matter, we can also count them, right? We can count them. However, when we talk about atoms or molecules, there's a lot of them and they're very, very small, very, very small. So you can't really count them. The way we overcome that is by using this concept called moles. And the assumption here is that one mole has 6.20 times 10 to the 23rd atoms or times 10 to the 23rd anything. So one mole is this number. It doesn't matter what it is, if it's atoms, pens, molecules, whatever. The same thing that a dozen is 12, no matter what it is. One mole is 6.02 times 10 to the 23rd of whatever. The one point I wanted to make is that this number is extremely large, right? 23 stands for zeros behind this number, so it's a really, really large number. Okay, so we can move from weights to moles, moles to weights easily by relying on a periodic table. So here you have a periodic table. The numbers that you see at the bottom, okay, the numbers that you see at the bottom, they're the weight of those elements per one mole. So everything in this periodic table is measured in terms of weight per one mole. So that is a key information for you to know. For example, one mole of carbon weighs 12 grams. Okay, so that's how you would read it. In the 12, you can see the 12.001 grams to be more specific. All right, so then we need to talk about converting from moles to grams or grams to mole. So here's our first problem. So the question is asking how many moles it's supposed to be are in 3 grams of carbon. Okay, so let me start annotating here. Every time, and I say this over and over again, but I'll say it again, anytime you see how many, you know that whatever comes after is what the problem is asking for. So how many moles? So the problem is asking for moles. So the problem wants moles, okay, moles of carbon, and given is anything else that's in a problem that's, well, given. In this case, it's 3 grams of carbon. Okay, so this is your given and this is your want. So using our, let me put it over here and then I'll do it again. So remember our dimensional analysis is this train track set up here where we set up here as given, we set up here as want, okay, and this it leaves it blank, and here's your conversion factor that we're gonna add. Okay, so keeping that in mind, I'm using a different color so you can see the separation here. Let's do that in here. Oops, can't draw a straight line for the life of me. So the given's 3 grams of carbon. Okay, what the problem wants is moles of carbon. Okay, that's what the problem wants. I need to find a conversion factor here. So as I said, when I showed the periodic table, I said that, hey, 1 mole of carbon weighs 12.001 grams. Okay, and you can double check me. You can go into your periodic table and see 12.001 grams. That is the mass of carbon. So now we can just go ahead and make sure that this is correct. And I know that this is correct because this unit needs to cancel with this unit. Okay, key information. Grams of carbon needs to cancel with grams of carbon. Okay, so now if I can take this out of this weird setup here, this is just to make sure that I know what's dividing what. I can see that 3 times 1, this is a multiplication, right? 3 times 1 divided by 12.011. Okay, so if I do this calculation, pretty much 3 divided by 12, I get something like 0.25 moles. Okay, and that is the answer to the problem. So you can rewind, pause, try it on your own to make sure that you understand. You might want to rewind and try it again, or listen to it again, or you might want to rewind, pause the video, try to solve it, identify what is the key information. So the molar mass of carbon would be the key information here, and how you set up your dimensional analysis would be a key information as well. So interact with the video the way you see fit. We are moving on. Okay, so this is another problem. So how many? Okay, that's my operating sentence or my operating term. How many? Whatever comes next gotta be the want. How many grams of, we're talking about water. How many grams of water are in? Are in meaning that this is my given 0.2 moles. And we are only talking about water at this point, so everything's about water. Okay, so I set up my dimensional analysis where my given is here 0.2 moles, okay, of water. And I know that I want grams of water. Okay, and the next step here, I need to go to the periodic table and find the molar mass of water. Now I guarantee that at least a couple of people would be inclined to be spending the entire life looking for water as an element. And I will be like, hey, realize that this is an atom. This is an atom. So water in reality is, make a different color. Water in reality is 2 hydrogens bonded to an oxygen, right? This is what water looks like. So we need to include all the different masses here. So we have 2 hydrogens, okay? And we can think about the weight of the hydrogen in a second. 2 hydrogens, and we have 1 oxygen, okay? Now the weight of hydrogen, now I can look at the periodic table. The weight of hydrogen is 1.00 I'm just going to abbreviate, it's 1. And the weight of oxygen is around 15.999, abbreviating to 16, just to make things easier, but you can keep the whole set of decimals. Okay, I'm just abbreviating here because I'm not using a calculator, so it's easier for me to do the math. So here I'm going to put 1, here I'm going to put 16. So the total amount here would be 18 grams per 1 mole. So now I can plug this in into my equation. I can say, hey, there's 18 grams of water per 1 mole. You might wonder why I did the way I did. It's because this unit needs to cancel with this unit. Okay. So I can abbreviate this by doing 0.2 times 18 divided by 1. And the answer is 3.6 grams. Okay. The one thing I wanted to mention is this problem is the same setup problem as before. The only two differences here, one is backwards. The other problem asked for moles and gave you grams. This one is asking for grams and gave you moles. The second one is on the other problem, I asked for you to solve for pure carbon, so you did not need to calculate molar mass. Okay, molar, let me write this down. Molar mass. Okay, this is what we did. This is molar mass, right? But in here you had to because it wasn't an atom, it's a molecule. All right. If the substance is a gas at standard pressure and temperature, we assume that 1 mole of gas occupies 22.4 liters of space. So that makes our life way easier. How so? Well, let's do this one. How many, hey, keyword or key term, excuse me, keep calling it a word. The want is moles. The given is 3 liters of carbon dioxide. Okay, no, this is carbon dioxide as well. The one thing that I forgot to put in the problem, and maybe since that we're doing this way, um, gas. Okay, so carbon dioxide gas. That's going to be a keyword here because anytime we're talking about gas, we're just going to assume this. If substance is a gas, this is the conversion factor that we'll be using. So we set up the same way as before. Okay, so I put here 3 liters of CO2 in here. And what I want is moles of CO2. Instead of going in the periodic table, looking for the molar mass of carbon dioxide, I'm just going to assume that, hey, there's 22.4 liters of any gas in 1 mole of that gas. Okay, so this is the conversion factor that you need to use for gases. So if we do that, we just take 3 times 1 divided by 22.4, and the answer will be 0.134 moles. Okay, so it's much simpler if we using gases. It doesn't matter what gas it is. This is the conversion factor that you'll be using. Okay, so if a substance is a solution, okay, then we must use concentration in terms of moles of solute per volume of solution. And this is the formula that we need to use. We call it molarity, is moles of solute per volume of solution. Notice that the units are quite important. It needs to be moles per liter. So let's solve this problem. So if I mix 1 mole of sodium chloride with 2 liters of water, what will be the concentration of the solution? Well, let's start with the want and a given first. Want and given. Okay. He wants concentration. Just concentration, which in this case would be the big M for molarity. The given is 1 mole of solute, okay, per 2 liters of solution. Usually water is the solvent, is what's dissolving things, right? So it's a little bit of salt added to water. So the salt is the solute, the water is the solvent, okay? And it's telling that because the salt is just a small, very small amount, we just consider that the volume of the water is the volume of the solution. It's not always going to be that case, but in this case it is. All right, so then the first thing, once we figure this out, the second thing that we do And I suggest that you work through those problems very methodically, do step by step, no matter how much you think you know it. It just avoids you from making mindless mistakes. Put in the formula, that's your second step, moles per liter. Okay, so that's your second step. Then your third step is plug it in. Let me use a different color. So here is moles, and here's liters. Okay, so I take 1 and divide it by 2, and I get this 0.5 moles per liter. Okay, and that's my answer. Okay, this is the next problem. If I mix 1 gram of sodium chloride with 2 liters of water, what will be the concentration of the solution? The same problem as before, except that previously I gave you moles and now I'm giving you grams. Okay, but the setup is the same. You're still looking for the same thing. So let's go step by step again, starting with the want and a given. Well, what he wants the same thing as before. He wants concentration in molarity. And the given here is 2 liters of solution for the reasons I mentioned before. Go back and rewind the video and listen to it again if you need some more clarification. And then 1 gram of NaCl, which is the solute, right? Then the next step is to plug in the equation. M equals moles over volume, and the volume needs to be in liters. Then here we go, let's plug it in. Okay, I don't have moles. That's going to be a problem which can be easily solved, but I do have liters, it's 2 liters. So what to put in here? Well, you need to put moles, but it's giving you grams. So think about the problems that we solved before. So you need to go back and solve that problem before you can do this one. So let's do a kind of like a side note, and let's make the side note green. Okay, so here we have step 1. Here we have step 2. This is going to be a step 3. Okay, so in step 3, and I'll do this quickly because if you want, you can go back to the previous problems to see how I put this together. 58.44 grams in 1 mole. Okay, this is the molar mass of NaCl. Go back and look at the periodic table to figure out that how I got the 58.44. You just need to add the 2 masses, one of Na, one of Cl, right? And if I do that, I get a very small number. Let me get my phone, and because I don't think I can do this on top of my head. Get a calculator going, and I have 1 divided by 58.44, and I get a very small number. Let me write it down. 0.0171, and that's going to be moles. Now this is going to be the number that's going to be here. So let me go do it in black. So now we go to step 4 to actually be able to solve it. Okay, so it's going to be 0.0171 moles. Okay, and then dividing this number by this number, I get an even smaller number, which is 0.00856, and that's molar. So it's a very, very small number, and that is the answer. So it's the same problem as before, but you just had to take 1 step further and convert grams to moles. Okay. All right, and finally, we can also make dilutions. So dilutions involving having the concentration of the solution before versus in volume versus the concentration of solution after, right? Here's an example. If you have a strong coffee, you might take a little bit of the coffee and add some water to it, um, and you make it more dilute, right? So that's the analogy here. So let's solve one of those problems. So if I mix 5 mLs of a very strong coffee, say the molarity of coffee is 1 molar, with 45 mLs of water, what will be the new concentration? Just based on mathematically, I can tell that the concentration will be about a tenth of this. Why a tenth? Because 5 over 50 is a tenth, right? So just based on um, that rationale, I should be able to figure out the answer. However, we can put into the same setup as before. So once given, okay, what the problem wants is M2, or the new concentration. Okay, what the problem has given us was a lot of things. The problem has given us V1, which is 5 mLs. The problem has given us M1, which is 1 molar. And the problem has given us V2, which is 45 plus 5. Okay, remember we're talking about solution, not just the solvent. In this case, this does matter. Okay, so the second step would be to put into the formula, which is M1 V1 equals M2 V2. Okay, and then the third step is actually solving it, which would be 5 times 1 equals M2 times 50. And if I solve for it, I would end up with M2 equals 5 divided by 50, which guess what? It is a tenth, 0.1 molar. That's the answer to this problem. All right, so we're gonna switch gears a little bit and talk about, okay, so how do we quantify chemicals in a chemical reaction? So we use stoichiometry, which is a way to calculate quantities in a chemical reaction using information from the chemical formula. So I showed you this picture before saying that even though something might have the same weight, it might have different number of particles. So for example, the pound of feathers versus a pound of bricks, obviously there's way more feathers present than bricks, even though they weigh the same amount. The same thing can apply here. You can have chemicals with the same amount but different weights. So you need to keep that in mind. Why do I say that? Well, because when we talk about chemical reactions, we need to use moles. We cannot use mass. Okay, so we have to rely on moles because then we can actually count, right? We can somewhat quote unquote count. So for that, we need to look at mole ratios. Okay, so this is the chemical reaction that's taking place. And if I want to know what is the ratio of nitrogen to hydrogen, well, I would say for every 1 nitrogen, I need 3 molecules of hydrogen to react with it. Or if I ask, what is the mole ratio between ammonia, this is ammonia, and nitrogen, I would say, hey, for every 2 ammonia particles, I need at least one, not at least one, I need 1 nitrogen molecule. And the way I'm making those ratios is just by looking at the coefficients in front of the molecules. Okay, and I'll let you look at the third one. But this is going to be really important, not just for this, but also when we're looking at acid and bases, right? So mole ratio is going to come pretty handy. So keeping the mole ratio in mind, we can now solve problems involving chemical reactions. For example, how many moles of nitrogen do I need in order to produce 6.5 moles of ammonia? Again, this is ammonia. Based on just looking at the problem, right away I know that I need about half. I'll be needing about half of nitrogen. How do I know that? Well, because I'm looking at the ratio here, and it says for every 2 molecules of ammonia, I need 1 of nitrogen. 1 is half of 2. So looking at over here, if 1 is half of 2, 6.5, around 3.5 3 or something like that should be half of 6.5. So should be about half of this. So let's double check if the rationale between the ratios is not feasible to you. Again, go back to your dimensional analysis. So what's given? What's given to me is 6.5 moles of NH3. Okay, oops, NH3. And what the problem wants, it wants to know moles of nitrogen. Okay, now to solve this problem, I need to do my dimensional analysis, okay, which will be 6.5 moles of NH3, okay. Now, and I want a moles of N2, and I know for every 2 moles of NH3, 2 moles of NH3, I need one mole of NH2. So look at here, I'm dividing it. Didn't I say it was going to be halved? I forgot to actually do this. So let me do it right now. 6.5 divided by 2. Yeah, about 3.25 or 3.3. Okay, so it'll be 3.3, which is half of this number, right? So 3.25 or 3.3 moles, okay, of NH2. And that's how you would do measuring of different reactants or product involved in a chemical reaction. Okay, so in our next video, we'll talk about how energy is conserved in those chemical reactions.